Alright, so I hope that you had a wonderful and relaxing break. And we're in it now for 3 weeks, and then we get another one. Okay? So, we're going to start today Unit 5. Okay? Unit 5 is going to take us the entire month of December. Okay? So, on the sideboard I put down everything that when things are due, with the exception of one thing, and I'll talk to you about that at the end of class. Okay? So, we're going to have formative assessments, not this week, but the next 2 Tuesdays then, 10 and 17. We're going to have a quiz this week, Friday, and next week, Friday. Okay? And then we're going to have a test on the Friday right before break. Okay? We're out of the textbook this unit, so you don't need to bring your textbook with you to class until next year. Okay? Wink, wink, nudge, nudge. Education humor. Okay? But we will be there will be 3 homework packets in this particular unit. I'm going to give you the first homework packet on Thursday. It will be due the following Wednesday. I'm going to give you the second homework packet next week, Wednesday, on the 11th. It will be due the following Wednesday on the 18th. And then I'm going to give you the third homework packet on this Monday, the 16th, and that will be due on the 20th. Okay? So 3 homework packets this particular unit. Okay? Questions on that? Okay? I dug deep into the vault to find some new tricks too for this unit to try and just mix things up a little bit. And so today you'll get one of those tricks today. Okay? We'll talk about that towards the end. Okay? So Unit 5 is all about rational functions. Okay? Putting the fun in function. I love this stuff. Okay? These are awesome because you take this ugly, mean-looking thing and you get a nice, pretty graph out of it. Okay? Okay? We're going to graph this unit. It's all going to be all about graphing rational functions. Okay? That's our goal. By hopefully before sometime after the 16th of December, because that's when the last thing that we have to teach you on rational functions is on the 16th of December. So after that, it's going to be great. Okay? It'll be good. Okay? So before we start today, I'm actually going to jump ahead a couple of slides, and I want you to get out. So most of you have started your notes, which is good for today, but I want you to have 2 pieces of paper out. One is going to be completely blank. The other one is going to be where all your notes are. Okay? If you're in a spiral notebook or a notebook, rip it right out. Yep, rip it out, because that blank one, I want you to have, that's going to be kind of your reference sheet, your go-to, that's where we're going to have, it's going to be kind of like a cheat sheet for you for everything that we do in this entire unit. We're going to fill that sheet up with 8 steps, okay? Because it's going to take us 8 steps to graph a rational function. Okay, and we're going to put those 8 steps on that front. So when you're doing those homework packets, you can have that out right next to me. Oh, I got to do this, then I got to do this, then I do this, then I do this, then I do this, then I do this. And then at the end, I can get it right. Okay? So if you wanted to write on there your steps to solving a rational function or steps to graphing a rational function on that separate sheet of paper, that's awesome. Okay? But we are going to be 2 separate things. Okay? All right. So first off, we need to take a step back actually to Unit 3. And in Unit 3, we talked about a rational number. A rational number is any number that can be written in the form of a fraction. A rational number is any number that can be written in the form of a fraction. So we could have fractions. We can have improper fractions. We can have whole numbers. Because 3 can be written as 3 over 1, 6 over 2, 9 over 3, etc., etc., etc. Okay. We can have decimals. We can have all of those. Okay. Can't have pi though. We had enough pi this weekend. Huh? Pi is irrational. Can't be written as a fraction. Alright? So, with that being said then, let's get the fundamental definition of this unit. And that is a rational function. We're going to be graphing rational functions. So let's define what a rational function is. A rational function is a function written as a... What? No. If a rational number is a fraction, what's a rational function? Function written as a fraction. Yep. Okay. Okay. So it's a function written as a fraction, where it's got a function for a numerator and a function for the denominator. Okay. P of x and q of x are polynomials. They're their own functions. Okay. Q of x is not the zero polynomial. Well, what's the zero polynomial? Anybody know? It's basically saying q of x can't be 0. Why can't q of x be 0? And why does that matter? No. Hey Siri, what's 0 divided by 0? Nope, come on. What's 0 divided by 0?
I'm on it.
Yeah, let's go. Let's get on it. Oh, I got no bars, that's why.
Stand.
No, you stand by. You should have had the old Wi-Fi on before. The Wi-Fi. Come on. There it is. And connect. There it is. Hey Siri, what's 0 divided by 0?
Imagine that you have 0 cookies and you split them evenly among 0 friends. How many cookies does each person get? See? It doesn't make sense. And Cookie Monster is sad that there are no cookies. And you are sad that you have no friends.
Yeah. So you can't divide by 0. Okay? You can't split something up into 0 parts. Okay? So that's why q of x can't be 0. Our denominator has to be something. Okay? Okay? So, what are these functions going to look like? Well, they could look as nice and easy as f of x equals 1 over x. Yeah, that's a rational function. It's a function written as a fraction. function on top, function on the bottom. They could look like f of x equals 2x minus 5 over x squared plus 3x plus 4. Okay? Or they could look really nasty. Huh? No matter how they look, we're going to treat every single one the exact same way. Huh? Whether it looks nice and easy like 1 over x, or whether it looks like that nasty thing that's over there on the right. Okay? Everything's going to be treated exactly the same. And what we're going to be talking about first is we're first going to be talking about the domain of whatever function it is. Okay? The domain of a rational function includes all real numbers except those that make the denominator equal to 0. Okay? Now, we're going to write the domain in a very specific way. Okay? So I'm going to start with a capital D for domain. And then I'm going to put a colon. And then I'm going to say that the domain is all real numbers with certain exceptions. Okay? Or certain conditions. And I'm going to list all of those conditions. So like in the first one, 1 over x. The domain of that is all real numbers, except x cannot be 0. Okay. The second one, it's all real numbers, except that one's not factorable. I should have went minus 3 there, or minus 4. Actually, what I should have done. You know, so we can find what those numbers are equal to. In that third one, I don't even want to touch that. Okay? Because there's 31 different exceptions there. Okay? So, the very first thing that we're going to do is we are going to set our denominator equal to 0 and then we're going to solve it. Okay. So in this particular case, we're using f of x equals 7 over x minus 2. So I'm going to say, well, x minus 2 is my denominator. So I'm going to say x minus 2 equals 0. And I'm going to solve that. Add 2 to both sides, and that gives me x equals 2. And that is my exception, my condition, my restriction, if you will. Because if x is 2, my denominator is 0, and 7 divided by 0 doesn't exist. Okay? So I'm going to write the domain here as all real numbers except x cannot equal 2. So what we're asking here then is what is happening with the function at x equals 2. So when I try and plug 2 in, what is happening with that function? That's my question of what happens when at these spots when the denominator is equal to 0. Anybody know from Algebra 2 what happens at x equals 2?
You plug in the x, you plug in the 2 into the x, and the denominator 2 minus 2 equals 0.
Right, we can't have that. So what happens there? Because we don't just stop at that point in time. And we still got to keep going. We got to push through it. Because we got to get to, we're building up to getting a graph of what this function is going to look like. So what happens to our function, 7 over x minus 2, at 2? Anybody remember? We get what's called a vertical asymptote. Okay? So if we go back up here, then we could say here that our vertical asymptote of this function is x equals 2. Couple of notes about vertical asymptotes. First, vertical asymptotes are lines. Which means if I ask you for a vertical asymptote in this particular case and you reply with 2, you are wrong. Because 2 is a number. Vertical asymptotes are lines. Lines are equations. In this case, vertical lines are x equals some number. Okay? So what you need to do then, if I ask you for what the vertical asymptote is, you need to say x equals 2. If you just tell me 2, you are wrong, and you are going to need to fix it. You're going to need to watch the video to figure out what that's all about. Okay? So it's a line that my function does not cross ever. Because if it crosses the vertical asymptote, that's saying that that function exists. Okay? If my function, if my graph crosses over a vertical asymptote, that's saying that this function works at x equals 2. But we just plug 2 in, and 7 divided by 0 doesn't work out. Okay? When we do put it on a graph, we're going to put it on our graph as a dashed line. We're going to get to that on Thursday. We're going to start graphing on Thursday. On Thursday, if we have a vertical asymptote, they must be on the graph. We don't get to not put them on the graph. They have to be. They're part of the function. Even though the function doesn't exist there, they're still part of the function. We find them in the restrictions or the exceptions or the conditions of the domain. And lastly, there can be more than one. We can have multiple vertical asymptotes. Okay? Separate sheet. Here we go. Okay? It's going to be our steps to graphing a rational function sheet. Okay? You're going to save a little space on your separate sheet. You're going to save a little space for step number 0. We'll get to step number 0 later on in December. Okay? So save a couple, 3, 4 lines for step 0. Okay? So for any function, f of x equals p of x over q of x, which is equal to a times x to the n plus something, 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 over b times x to the m plus something, 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 something. And whatever they look like. Okay? But we need, later on, we'll need to know what a and b are. Okay? Alright? So the first thing you're going to do, for now, is you are going to find the domain. And any and all vertical asymptotes. We do that by setting the denominator equal to 0. Okay? That's all for your separate sheet for today. Set it back aside. Okay? Don't be like the last class and then start taking notes on their separate sheet of paper. Okay? So we're back into notes now. Okay? So, find the domain and the vertical asymptotes for this particular function. Okay? Well, here is my function, f of x equals 1 over 2x minus 5. To find the domain, I set the denominator, which is 2x minus 5. I set that equal to 0. Solve that. I would first add 5, giving me 2x equals 5. I would then divide by 2, giving me x equals 5 halves. So the domain here would be all real numbers, but x cannot equal 5 halves. My vertical asymptote would be x equals 5 halves. That is step number 1. Okay. Questions on it? Okay. We're going to take a pause here for the cause. Okay. We're going to do some logic. Today and tomorrow and Wednesday and Thursday, the beginning part, are all going to be about logic. Okay? I'm going to make you think. Okay? It's all going to be number logic. Okay? So, if I take any number and I divide that by a really big number, or a bigger number, right? So, for instance, if I took 3 and I divided it by 1,000,000. Okay? So I took a number and I divided it by a bigger number. Okay? What's that going to be? It's going to be a really small number, right? Okay. What happens, here's where the logic part comes in. What happens if that denominator number, my big number, gets bigger? So, like, what would happen if I sent that bottom number, if I make that go to infinity? So that bottom number just keeps getting bigger and bigger and bigger and bigger. What you got, Chloe?
Smaller and smaller.
Until what? So it basically becomes 0. Yep. Okay. Will it ever go negative? No. No, because it's always going to be positive 3 divided by a positive number. Right? So this is going to go to 0. That fraction, essentially, if we could get to infinity, that fraction would be equal to 0. Okay? Fraction logic. The bigger your denominator gets, the smaller your fraction gets. Okay? Let's flip it around here now. What if I have got some number and I divide it by a really small number? For instance, if I said 3 divided by 1/10,000th. Number would get bigger, right? So that would become a big number. In this case, it would become 30,000, right? So that becomes a big number, right? So if I sent this now to 0, so that number gets smaller and smaller and smaller. What's going to happen to my number? Or the value of my fraction? 3 divided by 1 is 3. 3 divided by 10 is 0.3. 3 divided, or excuse me, sorry, I'm going the wrong way. 3 divided by 1 is 3. 3 divided by 0.1 is 30. 3 divided by 0.01 is 300. 3 divided by 0.001 is 3,000. Do you have your hand up? Nope. 3 divided by 1 over 10,000 is 30,000. It's going to go to infinity. Yeah, it's going to get ginormously huge. Yeah. Just like the toilets in Elf. These toilets are ginormous. Watched Elf once or twice this weekend. Yeah, so it's going to go to infinity. All right? Now, we do that kind of logic because of this next problem. This next problem says, first off, I want you to find the domain of f of x equals 1 over x. Well, how do I find the domain? Set the denominator equals 0. What's the denominator? What's the denominator? X. So x equals 0. Then what? I solved that. Done. Okay? So what's my domain? The domain is all real numbers. Except what? Except x can equal 0. Okay. Then it went on to say, find the vertical asymptotes. What's the vertical asymptote? X equals 0 because it's the restrictions in my domain. Again, Miss Stone, had you just said 0 there, I would have been all over you. Because 0 is a number, not a line. Okay? I know you're not going to make that mistake, though. Okay? Then it says, use logic to describe the asymptote behavior. That's what the function is doing near the asymptote. And the end behavior. Well, let's deal with end behavior first. Because we've already dealt with end behavior. We have some experience with it. End behavior says as x goes to infinity, my function goes somewhere. And as x goes to negative infinity, my function goes somewhere. Right? Okay? So let's talk about that now. So, as x goes to infinity, so that would be 1 over a really big number. Right? So 1 over a really big number from fractional logic tells me that that's going to be small, right? which means if I send it to infinity, it's going to be It's going to be 0. Okay? Alright? So this one's going to go to 0. Now my question is, if I send it to positive infinity, 1 divided by positive infinity is going to be what? Positive 0 or negative 0? It's going to be positive, right? Positive divided by a positive. So how we say that is we say that like that. We put a little plus sign up in the exponent of 0. What that's saying is as x approaches infinity, my function is approaching 0 from above. Means it's going down to 0, but it's never going to cross over. Okay? As x approaches negative infinity. Now, I've got 1 over a really big negative number. So it's going to go to infinity, right? So what's my function going to go to? My function going to go to 0, but it's 1 divided by a positive number divided by a negative number. So it's going to go to negative 0, which we say that as it's going to approach 0 from below. Okay. That's my end behavior. And yes, you have to have those pluses and minus signs on there. If you don't, Mr. Hannes, you are wrong. Okay? I'm trying to wake you up. Okay? No, you're not. I promise. I promise you're not. Okay? Alright? So that's end behavior. What the function is doing on the left and right side of my graph. Okay? Now, we've got asymptotal behavior. That's the new one for today. So this is what my function is doing now as it gets closer and closer to my asymptotes. Okay? So my asymptote is x equals 0. So now I would say as x approaches 0, what's my function doing? But there's two sides to 0, right? There's a left side of 0, and there is a right side of 0. For every vertical asymptote, I have two asymptotal behaviors. I've got a left side of the asymptote, and I've got a right side of the asymptote. Okay? And they are different. Sometimes they'll be the same. Sometimes they'll be different. Okay? So, as x approaches 0 from the left, so my numbers are negative, right? On the left side of 0, numbers are negative, and I'm getting closer and closer and closer to 0. So my number is getting smaller and smaller and smaller and smaller, but it's negative, right? So, fractional logic says 1 over a small number says what's going to happen? It's It's going to go to infinity. But because I'm on the negative side of 0, it's going to go to negative infinity. On the other side, now I'm on the positive side of 0, getting closer and closer to it. So now what's it going to go to? Positive infinity. Yeah. There are 6 answers to this one problem. Domain, vertical asymptotes, the 2 end behaviors, and the 2 asymptotal behaviors. Okay. Questions on this stuff? Making you think. It's all logic. And it'll get easier after Thursday. Because on Thursday you'll have the picture and you'll just be able to say, oh, goes to this, goes to that, goes to this, goes to that. Okay? So, I referenced this earlier in class today. I went deep into the bag of tricks. And so here is today's bag of tricks. I am going to give you this half sheet of paper. It's on retina burning red for a reason, so you don't lose it. Okay? You need to do this problem, so I would copy this problem down onto this retina burning red half sheet when you get it. This is your entrance ticket to class on Wednesday. Okay? Meaning you have one homework problem. Yes, it's got 6 parts, but you have one homework problem to do in the next 45 hours. I don't think I'm asking for much. Okay? However, if you choose not to do it, you don't get the opportunity to come to class on Wednesday. You'll sit in the hallway until you get it done. Okay? Alright? I'm not asking for much. Okay? I would also write down the instructions of everything that I'm asking for. Because if you don't have all 6 parts, you're not done. Okay? Think of this as your homework that's due the next class period. Except now, I'm not letting you in. You're sitting up there until you get it done. Those of you that are listening in off of the interwebs, because I forced you to watch the video, it's another reason you got to watch the video before you come to class too. If you miss class, you can just do it on a regular sheet of paper, and I would accept that too. Or if you lose your half sheet of paper, you can just do it on a regular sheet of paper.